Welcome guys to my channel. Today we're going to talk about symmetric groups and cycle notation. And at the end of the video we will understand that this picture is actually a 4-3-2 cycle in S9. So let's get started. So we start with a bit of notation and we write n bar for the finite set of elements 1, 2 up until n. And then for n bigger than 0 we define the symmetric group, which we write as Sn, as the group of bijections from n to n. So in a formula we have that Sn is f from n to n such that f is a bijection. Okay. So an element of Sn, which is called a permutation, is nothing but we write often sigma from n to n such that for all, let's say, I in n bar, there is a unique j in n bar such that sigma j is I. And multiplication in Sn is defined as follows. So given, say, sigma tau in Sn, then we define their product sigma dot tau as the composition sigma after tau as functions, and we go from n to n by using tau, and then we go from n to n again using sigma. So this sends I, it sends it first to tau I, and then it sends it to sigma I, sigma tau I. And we can make a mental picture for Sn as follows. So for, say, S9, you can think of 9 bar as just some points in a plane. And I've drawn here 3 examples, and I will give 3 different elements of S9. So for the first example, suppose that our permutation sigma maps 1 to 2. And then we think of 1 to 2 as a little arrow over here, indicating that sigma maps 1 to 2. And maybe 2 goes to 4, and maybe 4 goes to 3, and 3 goes to 1. Okay, and 5 will go to 6, 6 will go to 7, and 7 will go to 5, and 8 and 9 will be interchanged. Okay, maybe that is sigma. And then tau could be a permutation which maps 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 1. And it maps 7 to 8, 8 to 9, and 9 to 7. Okay, and the third one, let's say mu, it can map 1 to 2, 2 to 3, 3 to 4, and 4 to 5, and it maps 5 to 6, 6 to 7, 7 to 8, and it does nothing to 8, and it does nothing to 9. And as you can see, every permutation falls apart in a disjoint bunch of circles, and those are called cycles. And we can use this to write any permutation in so-called cycle notation. So let's do first the examples to get a hang of what cycle notation might mean. So we can write sigma as, so 1 goes to 2, 2 goes to 4, 4 goes to 3, and that's all the information that you need to know to see that this cycle corresponds to this little circle in my mental picture. But sigma has more little circles. It also has this guy, and that one we can write as 5 goes to 6, 6 goes to 7, and we close the bracket because 7 goes to 5. And then we also have 8, 9, because 8 goes to 9 and 9 goes to 8. Okay. Similarly, we can write tau as follows. So in tau we see that for this circle or cycle, we see that 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes to 1 again, so we close the bracket. And then we have another cycle over here, and we can write that one as 7 goes to 8, 8 goes to 9, and 9 goes to 7, so we close the bracket. Okay, so this one corresponds to that cycle, and this one corresponds to that cycle. Okay, and now finally we have mu, and well, we can write this as 1 goes to 2, 2 goes to 3, 3 goes to 4, and 5 goes to 6, and 6 goes to 7, and then we have 8 goes to 8, and 9 goes to 9. And what we often do is, because these 8 and 9s, which correspond to these guys, they don't add any information to this cycle notation, so we often just skip them and write this mu as follows, like so. So in general, it is a fact that we can write any permutation as a product of disjoint cycles. And if you look at the picture, then it's kind of clear why that is, because if you take any permutation and you trace where any element goes, then at some point, because you're in a finite set, you will get back to your element. For example, over here, if I start with 1 and I just keep on following where I go, so for example here, if I start with 1 and I keep following where I go, then at some point I end up with 1. So in general we can write any permutation as a product of disjoint cycles. This disjointness means that for example this point is only in this cycle, and this point is only in this cycle. So there are no cycles that have points in common. So we can, in general, this means that for sigma in Sn there are, say, tau 1 up until tau k for some k, such that sigma is the product tau 1 tau k, and with, say, tau I is a cycle x1 xn, and that means, sorry, no commas, just x1 up until xn, meaning it sends x1 to x2, x2 to x3, etc. up until xn minus 1 to xn, and then xn to x1 again. So the picture would be that you have like so, and you have x1, x2, x3, xn, and the permutation tau is this one, like so. And the disjointness means that if we have tau j is y1, ym, then xi is unequal to yj for all y and j. Okay, so sorry that it became a bit messy here. So an n cycle is of the form x1, xn. And in general, an n1 up until nk cycle is of the form sigma 1 dot 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 sigma k with sigma I and ni cycle. So if you go all the way back to the picture at the beginning, you see that this is a 4 cycle, this is a 3 cycle, and this is a 2 cycle. So let's finish with an exercise, and we're going to try to write the following permutation, sigma, in cycle notation, and this permutation maps 1 to 3, 2 to 5, 3 to 7, 4 to 8, etc. And the way to do that is we start with a 1, that is this one, and we see where it goes, and 1 goes to 3, so then we write down 3. And then we take this 3, and we see where that one goes, and we know that 3 over here is mapped to 7 over here. So then we write down our 7, like so, and then again we look at where sigma sends 7, and here we have this 7, and sigma sends the 7 to 1. So then we know that actually this 7 goes to this 1, and we said, okay, well then we close this bracket in our cycle notation. And then we take any number which is not in the cycle that we've written down already. So for example, we can start with 2, and then we trace where 2 goes. So 2 goes by sigma, goes to 5, so then we write down 5. And 5 goes by sigma to 4, so then we write down 4. And 4 goes to 8, so then we write down 8. And 8 goes to 2, so then we close our bracket. And now again we need to check where any element goes that is not already written down, but we can already see that 6 here goes to 6, and 9 here goes to 9, so we have 6 and 9. So this is your sigma, and as I said before, you can write this as 1, 3, 7, 2, 5, 4, 8. So if you want a mental representation, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And it maps these 1, 3, 7 and 2, 5, 4, 8. Here we have this 3 cycle, 1, 3, 7, that's a 7. And then we have here this 4 cycle, 2, 5, 4, 8, and 2 again. And then we have 2 1 cycles, 6 and 9. Okay, that's all for today. Thank you so much for watching, and see you next time.